Alright, so what we're going to do here is we're going to take a look at writing quadratic equations and functions given, some amount of information. And to do that, we have to start by taking a look and saying to ourselves, a quadratic function, it's really a parabola, which is a key point here. It's a parabola, which makes me think right away that I'm going to have something where there's going to be a graph involved. It may be opening upward, maybe opening downward, maybe really narrow, it may be, let's say, really wide, something like that. Again, the characteristics of the parabola are determined by the parameters in the equation. So our key in this problem is to really identify what's going on here. A, B, and C is our standard form. Our vertex form, which we also called completed square form, is A times the quantity x minus h squared, where h is the coordinate of the x value of the vertex, plus k, where k is the coordinate of the y value of the vertex. So a third form, though, that we're going to use, and it's frequently used, is, I call this root form. You can just call it x-intercept form, whichever. But I call it root form because you don't necessarily always have an x-intercept. They're the roots of the equation. Again, r1 and r2 are really the roots of this equation when set equal to 0. And sometimes those roots will be imaginary, so there are no x-intercepts. So I have a tendency to hold back on calling them x-intercepts. Anyhow, if we actually look at this form and multiply it out, here's what we're going to see. We'll end up getting here just simply a times the quantity x squared minus r2x minus r1x plus r1 r2 equal to 0. Okay, and again, how am I getting that? I'm just foiling, alright? First, outer, inner, last. Now, what you'll notice is if you go ahead here and take a look and you pull out a negative x in the middle, here's what you'll have. Because you're taking out a negative x, which makes both of these negatives come out here, leaving this as positive, positive. Okay, plus r1, r2, which we can clearly see, actually, is really this. Now, it's going to sound a little weird, but put a negative here, r1 plus r2. This doesn't change, I'm just reordering these two, which is fine. That's okay to do that. And that's simply because of the commutative property of multiplication. And now we can't forget about the x to pull out here, so we go ahead and write that in, and there's the x, whoops. There's the x right there, plus r1, r2. Okay, we close that up, equals 0. So, you might be looking at this right now and saying, well, what does this do for us? What this does, actually, is it allows us to look at the equation when it's in its standard form. So, let's go ahead and see. What we'll notice here now is that r1 plus r2, that quantity, is the sum, right, sum of the two roots. So we can call this the sum of roots. So we have a times x squared minus the sum of roots, okay, plus, now here what we'll notice is that this indeed is the product of the roots. So we write product of roots. Okay, and you can write out the words, I'm just abbreviating for now. So this is, again, the sum of the roots, SUM, sum of the roots, and this is the product of roots. So what we are able to do then is actually pretty amazing. We can align our coefficients up if we just, distribute this a through here. So let's go ahead and distribute the a. And what that allows us to do is say, okay, well, this is really just another way to look at standard form, right? Ax squared plus bx plus c. That's what that is. So that means that this quantity is really b right there. And, let's use green, this quantity is really here, right there. So just by looking at these, we can what's called equate the coefficients. A technique that is very useful. Equating coefficients, we get negative a times the sum of the roots equals b. That's equating these two, they're equal. And these are equal also. In this part, we're going to get a times the product of the roots is equal to the quantity c. Now, simply solve, and we have something that will help us here. We have the sum of the roots is equal to negative b over a. Again, I divide by negative a on both sides. Puts that down there. Here, divide by a on both sides. Just to show the steps. Okay, we had the product of the roots is c over a. Well, you might be asking one last thing, what does this all do? Well, this is what this allows us to do. We could say the sum of the roots is equal to some ratio negative b over a. While the product of the roots r1, r2 is equal to some ratio c over a. Now, for the rest of these problems here, this is the theory that we're going to use right here. So this is what we need to remember. Out of all this derivation, this is the key. And for a lot of these problems, it makes it easy to assume that a is 1. So whatever you get for the sum of the roots, just call that negative b, and whatever you get for the product of the roots, just call that c. Assume a is 1. And you'll see how it'll work out. I'll show you in the next example here. So let's take a look at example number 1. Example number 1 asks us to find a quadratic equation with the given roots, and it has integral coefficients. Integral, first of all, key word here, integral. If you don't know what it means, write it down, please. Integral means some integer value. So it has to be a whole number, but it could be negative or positive. But we're not going to be looking at coefficients that are like 3/4 or 1.2. Okay, nothing decimal or fractional or irrational here. We want integral coefficients. So let's take a look. So the sum of the roots is equal to negative b over a. So let's do the sum of the roots first. Sum of the roots is 3 plus I over 2 plus 3 minus I over 2. We're adding these quantities. So we have a common denominator of 2, so that carries over. Adding the numerator, 3 plus 3 is 6. Positive I and negative I cancel, leaving us 6 over 2, which is just 3. That's the sum of roots. Now, the product of roots here, okay, we have to think about here, multiplying these two quantities, we'll have to FOIL for sure. But what we'll notice here is that we'll definitely have an easy way to do this problem, remembering that there's a pattern. Multiplying the denominators, 2 times 2 is just 4. Multiplying the numerator, you would FOIL it out, but if you remember, the middle terms cancel when you're multiplying complex conjugates. So the first term gives you 9, the middle terms cancel, the last term gives you negative I squared. Well, negative I squared is negative 1. So this is minus negative 1. So it's 9 minus negative 1, which is really 9 plus 1, which is 10. So the product of roots is 10 over 4. So 10 over 4 reduces to 5/2. So this is the product of roots, and this is the sum of the roots. So let's go ahead and write this into our equation now. So remember, assume a is 1, so this is like really over 1, that's a. And this whole fraction is really over 1. Okay, 1 is the a value. So this is like your c over a, and this is your negative b over a. So by doing that, what we get is the following. Assuming a is 1. So again, why is b negative 3? Remember, the general statement said this. A times x squared minus the sum of roots times x plus the product of roots equals 0. Okay? So this is minus the sum of roots, so the sum of roots is 3. So minus the sum of roots, the sum of roots was a 3, so put a 3 there, and you get negative 3x, and this is a plus. Anyhow, we want integer coefficients or integral coefficients, so let's multiply everything by 2. Give us a value of a for 2, b for negative 6, and c for 5. Again, identifying a as 2, b as negative 6, and c as 5. In example 2 here, the question asks us to find the roots of the equation and check the answer using the sum and product of roots theorem. So let's start by looking at finding the roots. First, we know our formula for the quadratic formula is x, or in this case y, equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative b plus or minus the square root of b squared minus 4 times a times c Extend this root all over 2a. And what this will give us for the roots is negative 1 plus or minus root 41 all over 4. Alright, well, these are our roots right here. So let's go ahead and find the sum of roots and product of roots and see if they give us the correct values in this problem. Remember, the sum of the roots is negative b over a. So for the sum of the roots, we should get negative 1 over 2. Again, negative b is negative 1. There's a 1 there over this. The product of roots for a problem like this is going to give us c over a. So negative 5 over 2. Okay, and that's going to be c over a. So anyhow, let's find the product of roots and let's find the sum of the roots and see that we get negative 1/2 and negative 5/2. Let's go ahead and go to the verification. So for the sum of the roots, we have negative 1 plus root 41 over 4 plus negative 1 minus root 41 over 4. Notice I didn't even take the value of root 41. You'll see why. When I add these together, I have a common denominator of 4, so that stays. The numerator, negative 1 and negative 1 adds up to give you negative 2. But notice this cancels. This is positive root 41, this is negative root 41. So negative 2 over 4 is really just negative 1/2. Verifying from earlier, our statement, negative 1/2 for the sum of roots. Well, same thing right here. Negative 1/2 for the sum of roots. Let's go on to the product of roots. For the product of roots, it looks identical, except now we're just multiplying. And for this one now, what we're going to see, let me move this up if I can. Of course I can. I'm going to cross it off for now, even though we did just get the answer. This turned out to be negative 1/2 for the sum of roots. For the product of roots, though, 4 times 4 is going to give us 16. But what we're going to notice here for the numerator, though, we're going to FOIL this out. When we FOIL the first term, negative 1 times negative 1 is just 1. Then the inner term is going to be root 41 and negative root 41. Those are going to cancel. Remember, those are the middle terms. Because this is multiplying out to binomial conjugates. When you do that, the middle terms always cancel. But then when you multiply positive root 41 and negative root 41, you're going to get negative 41. So it's 1 minus 41 all over 16. Again, 1 minus 41 all over 16. So it's going to be negative 40 over 16. Well, those are both divisible by 8. This becomes negative 5 when you divide it by 8. This becomes 2. So c over a should be negative 5 over 2 for the product of roots. And take a look. Negative 5 over 2 for the product of roots. For example 3 here, we're asked to find a quadratic function with a minimum value of negative 3, whose graph has x-intercepts at 1 and 3. So let's start right away by sketching to see what's going on here. Okay, minimum value, negative 3, with intercepts at 1 and 3. So here's the intercepts. We know those where they are. 1 and 3. So the graph either looks one way or the other. Either it's going to open down, like A, or it's going to open up, like option B. It's one or the other. But since it says that it has a minimum value, it means that it has to open this way. This is a minimum. So we choose the red line. So the green line is not correct. So let's erase the green line here. I'll put the other part back in a minute. Anyhow, we have the red line that's important now. Okay, this is what it looks like. It's got to look like this over here. So the minimum value is negative 3, so this must be negative 1, negative 2, negative 3. There's the minimum value. Remember, the value of the minimum is the y-coordinate, how deep or how high or how low it goes. The location is the x-coordinate, and it's pretty obvious what the location is. But just to verify, notice the location is, again, on the axis of symmetry, which goes halfway between the roots. Remember, the roots are halfway between the axis of symmetry. So this root is 1, this root is 3. So if you want to find the midpoint of 1 and 3, just add them up and divide by 2. It's the average. It's just 2. So this point here is really 2, comma, and remember the value is negative 3. That's this y-coordinate right here. So it's 2, negative 3 for the vertex. So we could do this problem two ways. We can go to vertex form, or we can use what's called root form. You've seen vertex form already, and you have the vertex right here, and you could use 3, 0 as another point, or 1, 0 as another point, and use vertex form. But for this kind of a problem, what I'd like to do is look at this with the root form first. We'll do one, we've done one with vertex form before already. So let's go ahead and take a look at root form now. And by the way, the one that we did with vertex form was in our previous lesson. So here for root form, remember that it's y, okay, or in this case we could say f of x, doesn't really matter. We want the function though, I think it said, let's see. The original problem asked us, find a quadratic function. Yeah, function. So let's go ahead and find the function. So remember it's a times x minus root 1 and x minus root 2. Again, here's root 1 and here's root 2. We also know that we have a point. Here's our point, 2, negative 3. So let's go ahead and plug that in now. Negative 3 goes there, and the 2 goes in for x. Everything else I'll write in red still. Okay, so again, this green part comes from this part for x right here, and this goes in for y right here. So let's go ahead and solve for a. Negative 3 equals a times 2 minus 1 is 1. 2 minus 3 is negative 1. So we're going to end up with a negative 1 on the right-hand side. Canceling out our negatives, making those both positives, just getting rid of them. We get 3 equals a times 1. Okay, or a just simply equals 3. If a is 3, our answer looks like the following. F of x equals a times x minus root 1 and x minus root 2. Okay, that's our answer in root form. Well, you know what? Make sure we just, keep this in mind. SAT sometimes gives answers in standard form, so remember to do this now. This is definitely an SAT question. Okay, and then even possibly think about distributing the 3. But again, it depends on what the choices are. Okay, if the choices are given in root form, just stop there. But if you see everything in standard form, you would have to go ahead and do this. So again, distributing the 3 to each term. Okay, so this would be our answer in standard form. The other one would be answer in root form. You could also find the answer in vertex form by using the vertex that we talked about a minute ago. And that's what you do on the SAT. You look at your answer choices, see what form they're in, and then realize what form you need to go to. These both answers were given in root form here, in standard form over here. We could also have gotten the answer in vertex form. And if you want to try this in application on your own, go ahead and please try that. In a case like that, if you did go ahead on your own, I'll let you go ahead and try to find the vertex form answer. What you end up getting is the same a value actually in the front, and then x minus h, which is the center, or the location of the vertex, which is 2. And it was 2 comma negative 3, so it's plus k. So it's plus negative 3. And that really looks like this. A, x minus h, plus k, we could just write that as minus 3. Okay? Next problem. For the next example, we have a rectangular chicken pen. So imagine there's chickens housed in a little pen. Okay? And, it's a pretty big pen. They're allowed to roam freely. 60 meters of fencing. It's a lot of fencing. So they only have to be there. Maybe they're getting transported, whatever it is. So it's constructed alongside of a house. And the house has 60 meters of... the pen has 60 meters of fencing. So here's the house. Here's the pen. 3 sides. It's alongside a house. So we've got 2 sides here. We've got a 3rd side right here. Now, for a problem like this, we have to say to ourselves, alright, well, if the house serves as one side of the pen, it has to determine the greatest possible area that can be enclosed. So we're trying to find the area. Remember, the area is the length times the width. So here's the area. So we have an area function. It's x times y. And we want to find the maximum value, the greatest possible value of this area. So this is really like, this is your function over here, f of x, and this is x times y for now. The problem is we have x and y. We need to get rid of y, we need to have x's. So let's look at our perimeter. We know that the perimeter is 60 meters of fencing, it says. We have 60 meters. So we have 2 x's for the perimeter and a y. So 2 x's and a y is the perimeter. So let's go ahead and solve for y. So y is 60 minus 2x. Now we can take this and plug it in for y right there. to find an area function in only x, which gives us. So this is a function for the area only in terms of x, which means that we can now write this as a function like this, an area as a function of x. And clearly we can distribute the x and put it into standard form. So what this allows us to do is it allows us to take a look at the standard form of this equation. And if we want to go ahead and maximize the area, we have to take a look at this problem and say, well, where is the maximum on this curve? Well, this curve has a negative a value right here. Here's the a value is negative 2. The b value is positive. So we're going to have some function that is going to open down because there's a negative a value. So it's going to look like that somewhere. Forget the graph for now. Totally forget the graph. The graph will look like this, though, here. There'll be a maximum value. We want to find the maximum. Remember, the maximum value has the axis symmetry running through it. So let's go ahead and look for the axis symmetry. We'll work our way backwards. To get the max, we need the axis symmetry. So let's find that. Remember that the axis of symmetry is x equals negative b over 2a, which is negative 60 over 2 times a, which is negative 60 over negative 4, which is positive 15. That tells us that the x value for this garden is 15 meters when it's at a maximum area. So this is 15 by 15 already. So if that's 15 by 15 and there's 60 feet of fencing, that means that's 30, or meters of fencing, that's 30. So what's the area going to be? Well, it's 30 times 15, which is just 450. What are the units? Square meters. Well, we could also do this by taking the axis of symmetry and plugging it into the area function to get the value of the vertex. Okay, the value. Here's the 15 over here. And now we want to find the value of the vertex, the height, whatever this is. So we can say a of 15 is the same thing as just multiplying 15 times 30. We'll plug it in. And we're plugging into a function to evaluate now, instead of back into the geometric figure. I'll put a little line here to show that what we're doing. So this a of 15 is the maximum value. Remember, the value is the y-coordinate. It's when you plug in the x value. So here we're going to get negative 2. 15 squared is 225 plus, now 60 times 15 gives me 900 clearly. So for a problem like this, we have a solution. The area function is maximized when x is 15 meters, the width of the pen, and the value of it becomes the following: 450. And remember, it's area, so it's square meters. And take a look. Our answers check out. 450. Either you plug it back into the figure and just multiply the two, and you get the answer, or you simply plug the location along the x-axis of 15, which is really the x value, into the function. You do a of 15, and that'll give you the maximum height of the function. That gives you the vertex. So really, 450 is the vertex of this graph. That's what this question mark is. It's 450. So this vertex is 15, 450. Alright, next example. This problem says a ball is thrown vertically upward with some initial velocity of 12 meters per second. Its height after t seconds is given by h of t equals v naught t minus 4.9 t squared. Determine how high the ball goes and after how many seconds this occurs. Well, same kind of problem. We want to find the value of the function at its max height. So remember, the value is the y value. But to find the max value, we have to find the axis symmetry first. Because clearly, again, if we write this in the correct order, it looks like the following. So what we're seeing here is that when written in standard form, it's definitely going to open up downward again. And we're trying to determine how high the ball goes, which is the maximum value. And we want to know after how many seconds does this occur. Well, after how many seconds does this occur, this is clearly a function of time. That's along the x-axis. So what we're doing is we're plotting h versus t. So we need to find what the time is when this max value occurs and what the height is. So we go ahead and look for the axis symmetry. Negative b over 2a. Now it's always x equals, but x in this place is t. So t equals negative b over 2a if calculated, we get an axis of symmetry of 1.2. Now this is time, and it's measured in, look at the velocities, meters per second, so time is in seconds. That's after how many seconds does this occur? After 1.2 seconds. Okay, so let's go ahead and look at this here. On our graph, this is 1.2. So now we need to know what the height is. So we need to know what the y-coordinate is. So just plug this back into the function right there. When we plug it back into the function, here's what we're going to get. We're going to get h of 1.2 equals negative 4.9 times 1.2 squared plus 12 times 1.2. Remember, this is some negative quantity here because you're going to square this first. This is some positive quantity. The positive quantity better be bigger than the negative quantity to give us a positive max height. Remember, this is height, and the velocity was measured in meters per second, so this is in meters now, and that's the max height. So on the graph, if we're looking at this, this is 7.3 meters on the graph. Okay, and that's determining how high the ball goes, 7.3 meters. So as a verbal statement, we would say the max height of the ball is 7.3 meters, and this occurs after 1.2 seconds. Okay, then the last problem here. In this problem, we're asked if the production cost function developed by workers at a video game company is represented as C of n equals 2.1 times the quantity n squared minus 3.5n plus 4.7, where n is the amount of games sold in millions and C of n is the company cost in $10,000s of dollars. We want to determine the amount of video games that should be produced to minimize the cost. Then we want to know what is the cost for that game production. So let's find out how many games we should actually make to minimize our cost. Now, some problems will ask you to minimize cost, some will say to maximize profit. We've been doing a few with maximization, so I thought let's try one with minimization where you minimize the cost. It costs you to make a product, and that's usually what you do. It's called an objective function in engineering. So that's what we're going to do here. So let's take a look. If we want to minimize a cost, we have to think about what the minimum value is. To do that, again, we look for the axis of symmetry. So let's write this out by distributing the 2.1 first. Okay, distributing this 2.1 to each term, distributing, distributing, and distributing. That's what we're going to get. So we go ahead and look for our axis of symmetry. N equals negative b over 2a. Negative b, so it's negative negative, which makes that a positive, over 2a. So in this kind of a problem, over 2a, where'd the a go? Let's fix that. We're going to end up getting an answer of 1.75. And remember, n is the amount of games sold in millions, so 1.75 million games are going to be sold. What is the cost for that? So determine the amount of video games that should be produced. Here's the amount of video games that should be produced, 1.75 million video games. The amount of video games produced. And then we want to know what is the cost for that game production. So now we have to plug this into the function, the cost function, to find the actual cost. So let's just do that. Here we're going to get is C of 1.75. Well, that's just the function evaluated at 1.75. Remember, that's in millions, but we're leaving it as 1.75 as the function, because that's really the n value, 1.75. And if you multiply these out, what you're going to end up getting here for C of 1.75, the cost when 1.75 million games are produced, is around 3.43. And remember, if we go up, and that is in 10,000. C of n is the company cost in 10,000s of dollars. So 3.43 10,000s is 10,000s of dollars for each of those. So it's really 30 and 10,000 if we remember to move it over the correct way. We're going to get 34,300. Okay, so multiply this by 10,000. You multiply 3 by 10,000, you get 30,000. So it's got to be a little over 30,000, 34,300. Remember, there's 4 zeros here. So we move the decimal 1, 2, 3, 4 spots, put 2 zeros there, and there's your number you got right there. So this is going to be the cost for the production company, and this is going to be the amount of video games produced.